In the last section, we started talking about entropy. Remember, entropy was a measurement of disorder or randomness. Now, the second law of thermodynamics says that if a reaction is spontaneous, or any process that's spontaneous, there is going to be an increase in entropy in the universe. Now, it's not necessarily an increase in entropy in our system, so be aware of this. But the overall entropy in the universe is going to increase, okay? Now, when we're talking about the universe, remember we've got our system, which is our actual reaction or change, but we've also got our surroundings. So when we're talking about the universe, even though we may see more order in our system, as long as there is a greater change in disorder to the surroundings, it will still be spontaneous, okay? So this table has some information about how to determine whether or not the entropy is going to be increasing or not. You may want to take some time to look at that. It's not really something you'll need to know. We'll spend a lot of time actually calculating entropy changes and how that works, so don't really worry about that for now, okay? Now, when we talk about spontaneity, we're going to be talking about our delta G, and there are several factors that we said before that affect our delta G. The first is enthalpy, and remember our enthalpy is measuring our heat at constant pressure. So when we talk about enthalpy, we see it as an H, but it's also that Q at constant pressure, okay? If we have an endothermic reaction, our delta H is positive because heat is being absorbed by the reaction. In an exothermic, delta H is going to be negative because heat is being released by the system. Okay, now we've got this equation that looks pretty complex. We studied it before in a previous chapter. When we have our delta H, we can calculate it from a list of table, or a table with a list of values. So we can have something that looks like this that has standard delta H values for our reactants and our products. So what this equation is showing us, the N represents the number of moles. So I'm going to multiply the number of moles of my product, and I'm going to do that for each of my products. This little symbol there, epsilon, is the sum of. So the sum of the number of moles of my products times the H value for my products minus the number of moles of my reactants times the H for my reactants, okay? So the sum of my products minus the sum of my reactants. We did calculations with this in a previous chapter. I'm not going to spend a lot of time with it in this part of the video because we'll actually use this equation for delta S as well as delta G. So we're going to do these calculations in more detail. So if you don't really remember this right now, don't stress, we're going to see it again, okay? So we've got enthalpy, we've got entropy, and we've got free energy, okay? So what's going to happen in our system is it's going to move towards lower enthalpy. It wants to release heat, and it's going to move to higher entropy. It wants to be more disordered, okay? Now, Gibbs free energy, this letter G, we saw the reaction for it in a previous section, is the amount of useful work. Ignore that line. I don't know why there's an extra line. But it's the amount of useful work that can be obtained from a process at constant temperature and pressure. Now, what's important to remember about Gibbs free energy is it's going to tell us whether a reaction is spontaneous or not. If I have a negative delta G, my reaction is spontaneous. Now, the reaction isn't always spontaneous, but under these specific circumstances, this temperature, this pressure, these states, my reaction will occur without any outside intervention. So we saw this equation before. My delta G, my free energy, is equal to the change in my enthalpy minus the temperature, and this is important, this temperature needs to be in kelvins, times the change in entropy. Okay. Now, if you look, this table is important, okay? So what it's looking at is how my delta G value changes depending on my delta H and my delta S. So if I look at my first case, my entropy is positive, so I've got more disorder, and my enthalpy is negative, I'm releasing heat. More disorder, releasing heat, I am always spontaneous. Okay? Delta S is positive, so more disorder, but I need to absorb energy. Well, it can be spontaneous, but only at high temperatures. I need to have enough energy to make it go. It has to have enough energy for that to work. Okay? If my delta S is negative, more order, less disorder, that's bad, but I'm releasing energy. Again, it can be spontaneous, but this will only be spontaneous at low temperatures. Okay? If my disorder is decreasing and I need to absorb heat, nope, not spontaneous. It's not going to go on its own. Okay? So here's what the equation actually looks like. Here's my example. I'm asked, at what temperature is the following process spontaneous at 1 atm? What is the normal boiling point for liquid bromine? So I'm trying to change liquid bromine into gaseous bromine. I'm given my delta H and I'm given my delta S. Well, I know that delta G is equal to delta H minus T delta S. Okay? I'm trying to figure out at what temperature, so T is my unknown. So I'm going to start plugging in variables. Now here's the one thing we need to be super careful about when we're solving these problems. Delta H is given to us in kilojoules per mole. Delta S is usually given to us in joules. Those two things are not the same. We need to make our units equivalent. Now it's up to you whether you want to change joules to kilojoules or kilojoules to joules. Doesn't really matter. I like multiplying, so I'm going to change this to joules. So I've got 30, I'm going to multiply by 1,000, so 100 joules per mole for my delta J, or delta H. Okay? So delta G is equal to delta H minus T. I don't know what my T is, that's what I'm solving for, times delta S, that's 93.0 joules over K dot mole. Now, I don't know my delta G, but I do know that I want this reaction to be spontaneous. So I'm going to set this G equal to 0. Any temperature that's bigger than the one I get will give me a negative value. So any temperature above the one I calculate, my reaction will be spontaneous. Okay? So now I want to solve for T. Well, let's get T over to the other side. So I'm going to add this to both sides. So I've got T times 93.0 joules over K dot mole is equal to 30100 joules over mole. I want to get T by itself, so I'm going to divide both sides by 93.0. My joules will cancel out, my moles will cancel out. When I plug this into my calculator, I get that my T is equal to 324 Kelvin. At this temperature, my delta G is equal to 0. My system's at equilibrium. If I increase my temperature, then this becomes bigger, this becomes more negative, and so my reaction becomes spontaneous. So any temperature above 324 K will be, that's I, spontaneous. Okay, so those are how we do those calculations. Okay.